Okay, let's start, everyone. Thank you, everyone, for attending. This talk is about evolving HDFS to a generalized storage subsystem. My name is Sanjay Radia. I work for Hortonworks. I'm the chief architect there and one of the founders. I was part of the original Hadoop team at Yahoo since about 2007. I'm a Apache Hadoop PMC member and committer. Prior to that, I was at Sun Microsystems, a startup in India, and worked on data center automation, virtualization, Java, HA, OSs, things like that. Prior to that, I was at University of Waterloo, did my PhD from there. Okay, quick overview. We're going to start with a view of HDFS and what are some of the evolutions and changes in the past, what are the ones that are coming in the future, and the motivation for them. And then I'm going to focus on scaling HDFS. What do we do well? Where are the challenges, which is small files and blocks? And what are the solutions? There are kind of two parts to this. One is partial namespace, which is not the focus of this talk, but I'll briefly explain that so you see the larger model and how everything fits together. And then about block containers. And we are actually implementing block containers in a very generalized format, which is really what the focus of this large part of this talk is, storage containers to generalize the storage layer. And as part of that, we'll be solving this scaling problem that we have in HDFS. Okay, so give you a quick little bit of background because I'll be talking about two layers in this talk, the namespace layer and the block storage layer. So HDFS looks roughly like this today. It has a block storage layer at the bottom, which is basically the data nodes, and a namespace layer on the top, which is the name nodes. Most of you probably run a single name node. However, HDFS was extended a few years ago to do federation, and therefore you can run multiple name nodes. In fact, it can even run some other foreign namespace on the data nodes. So that's when we started the separation between the namespace and the block storage layer. And so think of those two layers as being kind of separate. The only thing that is a little bit bizarre here is that part of the block layer, which is the block management layer on replication of the blocks and block locations, etc., is actually done inside the name node as a library. It's not a completely separate library. It has still got some coupling to the name node, but it has been separated when we did federation. But overall, this is just roughly the layering in HDFS that you need to kind of understand to understand the main part of the talk. Okay. So going forward, if I look at this picture here, I've got three main dimensions, the horizontal and the vertical. And that has been the original design of HDFS, the original focus many, many years ago. In fact, it's been derived from the original design of the Google file system. So what was it all about? It was about supporting petabytes of data, and that's why it's called big data, by horizontally scaling large number of data nodes. Okay. And to be able to support a large number of compute clients. And we support anywhere from 60 to 100K cores of clients. And that's no easy task, okay? And as part of that, we also want to make sure things are really reliable. So the data nodes have multiple replicas. There's automatic recovery in the system. When a data node fails, a disk fails, it automatically replicates before you lose a second replica. So this fault tolerance built onto that. Later on, we added, over the last 5 years, HA, disaster recovery, snapshots, etc. Okay, so these three dimensions were the original core of the system. And, of course, there was work going on in performance as we improved over time the performance. And that's a dimension that's going to continue to work in any storage system as we add features and we make performance improvements. Okay, a thing that was added pretty soon in the early days was security. And what is unusual about this security, a lot of people don't realize it is not based on a pure client-server model because the Hadoop environment was not a pure client-server model. The fact that you have a virtualized compute layer on which you can execute jobs anywhere, the job executes after you have submitted the job, means that you're not there to sign in. And therefore, you need something like a delegation token. Whether you are running jobs or services in this kind of environment requires a slightly different security model. Okay. More recently, we enhanced that by having transparent encryption. Okay. And after that, or even before that, something called heterogeneous storage, so that HDFS understood different kinds of disk. It has some policies there. Okay. And then recently what we are working on is erasure codes to cut down on the overhead of storage. and that's in beta right now. And the other focus that has become recently is bad applications. So what we have is bad applications can go and really bombard this shared name node with a lot of seeks, reads, opens, creation of lots of files. So bad applications, when you have a set of cores that Yarn lets you just parallelize very easily, or Hive lets you parallelize, or Spark lets you parallelize easily, means you can really cause havoc in your cluster. Okay, in fact, HDFS does better than any other file system would in such an environment, but still it's a problem. So that's been a focus, and we've got some solutions on that. I'll just talk briefly about that. And we want to kind of move that towards a more multi-tenancy resource management isolation model in HDFS. And kind of mark that as blue because that's going to be more ongoing work. Okay, and I'm going to really talk now about the work that this talk is about. So one of the issues is now you're very fat data nodes with 12 disks, 24 disks, lots of 6 terabytes, 8 terabytes, and growing. And so you're going to have a lot of blocks, a lot of block reports. Then people are creating large number of files, small files, and blocks. And I'm going to talk about that. And file co-location is another thing that we want to support. And the thing that people often ask, can I do things beyond files? Why, can I do object stores? Can I do better support of HBase, for example? And so this bottom 3 blue lines that I showed is really the focus of this talk and how we do that in a more general way than just trying to solve a point problem, okay? And so that's what this talk is about. So just quickly to reiterate on recently we have had rich storage media policies and tiered storage. You can write policies to move to have one replica on SSD, rest on spinning disk. Storage efficiency as part of the tiered storage, you can have archival storage with lots of lower spinning disks and very few cores, and you can get a 6x reduction on your cost. For example, Erasure code, which is in the works right now, gives you a 2x cost reduction. As I mentioned, we added transparent encryption. A lot of work on operability, rolling upgrade support in HDFS in a more first-class way. Balancer improvements, data node liveness protocol, so that if you're a busy client, we don't start losing liveness with data nodes, so different channel port, make that work better. Reduce the number of data node messages to name node, again, to be able to scale better. But we're going to talk about how to really scale better in a more fundamental way in the rest of this talk. Improve block report processing, protect directories to avoid data deletion. We have people who said, oops, I am an admin. I went to /user and I said delete /user skip trash. And they do that and then come and say, I didn't take a snapshot. I said skip trash, can you please get my data back? What the fuck's going on with your system? It should be able to do this. And it's like, no, you cannot do this. If you're an admin, you can really cause, in fact, I do that on my system here. I can call Apple as many times as I like, they won't care. But what we did was to basically say you cannot go and delete the user directory unless everything underneath is empty. So you have to go manually delete every directory, and you could write a script to do that, in which case you really know what you're doing, and then don't come back and tell us I did a delete, skip trash. Okay, dealing with bad apps, so we have something called name node top, which will tell you who are the top users who are bombarding the name node. There's log tracing to figure out which is the caller ID inside the log, so you can figure out which is actually the bad job that is causing problems. And then there is fair call queue, which currently is only based on per user. So they'll ask clients to back off if they are overusing the system. Currently it's on a per user only. We're going to soon make it per job and tie it better into the Yarn resource management. And so this kind of recently what's happening in the system, in the HDFS system. And I'm going to now switch to scalability to motivate the rest of the talk and talk about the problems and the solutions. Okay. So what does HDFS do well? HDFS stores all its namespace metadata in memory. And a lot of people say, are you guys stupid? Why did you ever do that? Why did Google ever do that? But actually it was the right decision in order to support large clusters and thousands of clients. Okay. If you kept the namespace on disk, you would just not survive. Okay. So good news is it supported 60 to 100,000 K tasks, low latency, but it only kind of works if you have large data. You can support a lot of large data if your files are fairly large. Okay, and there are proof points of large data and large clusters in production today. So single organizations have over 600 petabytes on HDFS. Okay, single clusters with over 200 petabytes are using federation, for example, at Facebook. Okay, large clusters over 4K multi-core nodes bombarding a single name node. All this works. The metadata being in memory is the strength, but it's also the weakness because it doesn't let you scale to a large number of files and blocks. Okay, in order to, and so this challenge right now is about, so we can scale to about 350 million files. And if you want to improve on the number of operations, the number of files, the only solution currently available is federation. And what it does, it lets you add multiple name nodes. It is in deployment at Twitter. For example, at Facebook, I should have also put that in there, sorry. They have, clusters with 3 name nodes and over 5,000 node cluster. Sorry, this is at Twitter, that they have clusters with 3 names and want to scale over to 5,000 and then to 10,000 nodes. This particular code has been backported at Facebook to scale HDFS in production use there. Okay, so what are the way to solve this in a more fundamental way? So there are 2 parts to the solution. One is to scale the namespace, and the other one is to scale the block storage. So the idea here is to keep only the partial namespace in memory. That is the working set. And the good news is that if you're storing the last 3 to 5 years of your data on HDFS, really it's only a small portion that is actively used, which means that the working set fits in memory. But that doesn't mean you're going to go down to a 2 gig name node, okay? Because you really want your working set to fit in memory. And memory is cheap, so otherwise what will happen is you'll page. And if you page or swap your working set, then you will not be able to scale to hundreds and thousands of tasks bombarding it, okay? So that's the first part. Now, if I only keep, let's say I use the same solution to keep the block map in memory, and therefore I can have maybe, gazillion blocks. Unfortunately, that does not work. And the reason that does not work is that you get block reports coming periodically, and that in order to process the block report, you need to look at the block map and see which ones are missing replicas, which ones are not, update the block map, which means the notion of the working set completely blows out of the water. So every hour you need to go and bring in the full working set. And so that just will cause a lot of havoc on this idea. So the solution here really is to talk about containers of blocks. So not a single block, but a container that contains many blocks. So you'll have block container reports rather than block reports, which will reduce the block map, which of course we'll call it the container map, and reduce the number of container reports, okay? And that's kind of what we want to do, but we really want to extend the data now to support what we call generalized storage containers, not just block containers. And that's what I'm going to talk about in this talk, okay? Before I do that, give you a quick interlude on partial namespace and volumes to let you see how the whole picture fits together, okay? This is not the focus of the slide, of this talk, but I'm just going to present that briefly. So it has been prototyped. In fact, we had an intern from CMU did a whole bunch of benchmarks, studies on this. And the main thing here is that most file systems always usually keep a partial namespace, but they are not scaling to this scale. So for example, in Hadoop, we will have to really talk about cache replacement policies of the working set, because that's going to be very important in order to make this work, okay? So work is in progress in this space. The other thing to note is that partial namespace will allow multiple namespace volumes, and therefore that gives you a slightly different model on how you will use and federate and scale your system. So this kind of is the picture today. You have a set of data nodes and a set of name nodes, each with 1 volume. Most of you are only using a single name node with 1 volume, but this is the general model. Okay, so how does that change with partial namespace and multiple volumes? Okay, if you keep only the working set in memory, what does that mean? You can scale beyond the memory of the name node, which means I can now start offering you multiple volumes within a name node. In fact, you won't call it a name node, you'll probably call it a name server, which means that they're containers of namespaces. Okay? Now, you might have namespace volumes based on users, each user, or tenants, or databases in your system. Okay? Whatever you like. You might have policies and management policies tied to volumes. A lot of people have actually been asking for volumes. Because it helps them separate the data, manage the data differently, how to do DR on them, etc. And then you might have a mount table for your unified namespace, and there could be a central volume server from which you can create the mount space. So that's the general model you move to. It'll still mean that you can have a single namespace if that fits in your thing. And how many name servers will you have? So you'll say, the number of name servers I need is sum of the working set, okay, sum of the throughput that I want on my operations, okay, and you will move namespace for balancing the load, but overall that's what you have, okay. Now, if you find that you need more, then you will create a new server and move a volume there. Now, what don't we allow? We don't allow you to have a single volume spanning name server. And so if you cannot fit in a single namespace, remember with partial namespace, you're going to have a large number of files you can. If you cannot fit, then go to some other file system. At least I'm not interested in solving that problem. Somebody else in the community might, but solving a distributed namespace across servers is a non-trivial problem to keep it consistent and across renames and all that. So that's not what my company is focusing on, but the community does it, it may happen. Okay. The other thing you get out of this is n plus k failover. So I can fail over any volume to any other one. And the good news with partial namespace is that I don't need everything to fit. Okay. So that's the first benefit, that I can have something fit in there and do a failover. And when I start up, I don't need the entire namespace to be brought in. Slowly the working set can come in memory just like in a regular file system. So that works very well. And I can do n plus k, which means I can say these k servers are for failing over from these n name nodes. Okay, so I can play policies like that, or I can say for the production volume, this is where I fail. For the non-production volume, this is where I fail. Okay, and I can say non-production, I only have 1 or 2 failure or recurs. You can do all those models because the fact that now things can fit. If they don't fit, it's okay because yes, you might have some trashing, but that's only during times of failover and things like that. So it gives you a much more flexible environment in which to manage. Okay. So I'm now going to move to the main topic, which is storage containers, better HDFS and beyond. So this is how the picture looks. What I have on the bottom is the data nodes. And what I've done in the data nodes is I've got different kinds of containers. Containers storing blocks for HDFS. Containers storing objects for an object store. And so I've got an object store on the top. I've got HDFS on the top, maybe multiple volumes of them for different tenants. Might provide specialized HBase containers, table containers, etc. Okay, all of them are sharing the physical storage, so you don't need to go and decide how much who gets what storage. You'll have quotas on the volumes at the top. Sorry, on the services at the top to manage who gets how much. Okay, and which user gets how much. And so each of these containers can do something that is specifically optimized for that use case and that application, be it a file system or an object store. It can do indexing. It can do caching, and so we can support HDFS block containers. We can do co-location because containers of files that you co-locate can go into the same container. Can do an object store. You could do something like I want a single replica and then I want the next replica to be on S3 or some cloud storage. So you could use it on the cloud in a very different. All those things are easier for me because I have a container that can specialize to deal with those problems. Okay, and what it does is that it means there will be some common services, the green stuff that I just added, okay, for replication, consistent cluster membership, container location. You don't need each of these containers to build that on their own and kind of build that as a, and that's like the block management layer that you have today. So we need to separate that and make it a library. And there are other benefits. For example, it's a place where if I want to put new protocol enhancements to the block container, I could copy that code, have a block container type 2 or enhancement to the protocol, and then try that out, and then maybe fold that back in once it has been tested, etc., things like that, okay? Put smaller, riskier features in a new container. So it gives me a lot more freedom within the stuff in a production system for people to try out different volumes, things like that. So that's the general model that we want to move towards. So we want to solve the block container problem, but in a more general way, okay? So what does it look? So I'm going to show you the current world and the new world. So in the current world, I have a namespace. It's in the name node. A file is a list of block IDs. Okay, so it's an array of block IDs as I've shown. There's a block manager, which is also in the name node today. It has a block map. It says block ID to location. Location is an IP address of a data node. Then it does, what else does it do? It does pipeline repair. So if there is a pipeline being written, the block management layer, the name node works on repairing the pipeline, updating the generation number, and doing replication management. A data node goes down, replicate, a data node comes up, and I've got excess replicas, delete them, etc. Okay, the data sits still on the data nodes, and what does the data node do? It has block ID, you give it a block ID, it's got the data on the disk, it ships it to you. Okay. And there's other things like generation ID, as I mentioned, to deal with fail nodes. There is some complicated code in the name node about block completion, file completion, to deal with failure conditions, things like that. In the new world, namespace will still be in a name node or a name server. It'll be file goes to block IDs, but block ID now will have a container ID and a local ID. Okay? And then you will use that to route to a particular data node containing your container. And so there will be a container manager logically centralized, initially as a library in the name node, but later on could become a distributed service. And it's very easy to distribute this because what you have is a flat set of namespace called container IDs, and you can actually hash that, and you can use a lot of schemes to manage that. So there'll be a container map which will take you container ID to location. Remember, the block ID contains the container ID, right? So from there you get it, you do that. There is replication management that will have to do. A data node dies, replicate the container, arrange to issue those commands, and there'll be cluster membership of the data nodes which manage the containers. Okay. Then the containers sit in the data node, so they will have to contain the block metadata and the data, map the block ID to the data, do pipeline repair, block completion, and something equivalent of the generation number. Maybe we'll creep a generation, maybe it'll in fact become the epoch number in a Raft protocol because we may use Raft. So that's the old world, new world, okay? And as all solutions in computer science, what we have done is we've added a level of indirection called container ID, right? And you solve all good problems with one level of indirection. So that's kind of what the old one did, okay? So a container is something that sits inside a data node. It contains many, many blocks with different block IDs. Okay, I again recap the mapping that I just talked about. And a container can really be viewed as a local key value store, okay, except that it's got multiple replicas. Okay, there's the block ID is the key and the data is the value. Okay, so we've actually prototyped this right now. We're using LevelDB, and the block ID is of course the key, but the file name of the local file is the value because it's the easiest thing to get started. Of course, this does not work well for tiny files. So the optimization would be small blocks, for example, less than 1 megabyte could be stored directly in the RocksDB. Okay, other compaction for blocks to avoid lots of files can be done, but these are all things we could evolve over time. And so that means I could now have different containers and evolve that process over time much more easily. Okay, and so that's the model we are going towards. Okay, now the hardest part of this actually problem is not the part that I just explained. It's actually the pipeline and the replication. Okay, so today what do we do in HDFS? It's a data pipeline. It is forms for a chain replication as data is being written. Okay, and for its correctness, it depends upon a central coordinator to deal with recovery, to deal with things like generation ID, so that old blocks that failed in a pipeline have the old generation ID, new ones get a new generation, and so when the old one comes back, you can just throw it away. Okay, and so that kind of worked really well, and we don't really have a central coordinator. We do have the container manager, but we don't want the container manager to start now dealing with this lower level. Okay, so really we have kind of two solutions. One is to go with something like a Raft replication, and that's something that has been designed, proven to be correct and solve this problem. And up to now, it's been primarily used for small updates, transactions, and it fits well, extremely well for the metadata. If it's going to work well for the data, we need to see, we're trying to prototype this, okay, and we need to understand that. The other approach that is also kind of being discussed is a kind of a hybrid Raft and a pipeline, okay. And so you can think of Raft as, in fact, playing the role of the central coordinator and to have a data pipeline approach. So this hybrid stuff is also under discussion, and so we will be trying to address. This is the most difficult part of the problem. The rest of the stuff I've talked is not that complicated. As you can see, it was a fairly simple explanation, right? So this is work under progress. We are getting the design done. So we're going to write down the approaches, and we are going to post this as a Jira on Apache for community feedback, etc. Okay, and then kind of give people some of our feedback, prototype that we have, and post the prototype so people can take a look at that. So next steps overall in this evolution is remove the block management layer. Locking with because it has some really tricky locking with the namespace. In the short term, of course, it'll reduce the lock contention and actually will be of immediate benefit. But as we remove the tight coupling, it allows us to implement a cleanly separated block container management layer. Okay. The other one is the block container, and so initially our goal is to have 2 to 4 gigabyte blocks container sizes. Initially, okay, just because we believe that's what we should go with, and they'll give you a 40 to 80 reduction in block reports and block map, which means you will scale to a large number of blocks. Our goal is to go to tens of billions of blocks, over 100 billion. Okay, and this will also reduce the block report pressure on the name node. Okay, why 2 to 4 only? And so here it is. This is the unit of replication. If I increase this, I scale a lot better. But that means every time I have a failure, that's the amount I need to replicate. Okay, and it also means if I lose a whole data node, I have fewer places from which to do parallel replication. If you have a huge cluster, then I can use larger one. If I have a smaller cluster, then I do that. I don't have as much parallel replication. Today, HDFS, if you lose a 10 terabyte or a 20 terabyte data node, it can actually recover in matter of minutes, 5 to 10 to 15 minutes, or even less if you have a larger cluster. Like a 3,000 node cluster, you can recover in under a minute. Okay, and that happens because there's parallel recovery. You don't want to lose that property. Okay, so as network bandwidth increases, the size of this container will increase. Okay, the other one is partial namespace. Initially, we believe this will take us easily to 2 billion files. And as we get more experience in working set, etc., to billions of files, tens of billion, about 10 billion file per volume. Okay, and then we want to add volumes and n plus k failover, and then in parallel work on other kinds of container. Okay, so to summarize, HDFS kind of has the scale in terms of row storage and cluster size has been proven in real production system. I'm not talking about what are the number of bits inside a block ID and what can I theoretically scale to number of blocks. I'm talking about real production systems, okay? So over 200 petabytes in a single federated cluster and 30 petabytes in a single non-federated cluster, okay? Over 4K cluster sizes, but typo over their own number. But very large number of small files is a challenge. And that's what I kind of talked about in this talk. Partial namespace initially will scale to about 2 billion files and then to about 5-10 billion files per volume, as I mentioned. Block containers will help us scale to 6 billion to 12 billion blocks and then later to more. Okay, and we are the main thing about this is the way we implement block container really is in a more generalized fashion. And what we are doing is restructuring the storage layer to support generalized storage containers. And the goal here is to not just do a single solution for HDFS, but to do in a more generalized way so that it meets future needs of HDFS, but other needs also like an object store, better H-based support, things like a replica on S3 and another one on local storage and things like that you want to do in the cloud environment. So to allow us to kind of have a very strong basis on the bottom of the system to support this. So that's kind of what my talk is about. And this is what we are working on. And so questions and answers.
You told the better H-based support. Are you talking about directly writing H-based data to the blocks?
No, so that actually could be done even if you didn't have containers. So that is something, when we did federation, we were actually talking about having a tiny, HBase does not need the namespace. It doesn't need a large namespace. It doesn't need a hierarchical namespace. Okay, in fact, it doesn't need the goddamn name node there, right? So it would do a lot better with a simpler system. So yes, that in fact could be done today. Because once we did federation, we separate out this, we allowed you to have multiple applications on the top, like multiple name nodes and HBase. So there you could really have a tiny little mapping of HBases, H files to blocks, and you could solve that problem. So yes, that is true. So that you can do, in fact, today, and with this model, it supports it even slightly better. But what we are hoping is that we can actually do something more fundamental, like actually tell HBase that we can provide something in the middle so that you can have more direct access to the local disk. So kind of have a container so the HBase could say, you know what, I'm also going to have replicated containers and I manage the replication. So we could start moving towards that model. It's actually a lot trickier than the other two examples I gave. Object store, and that is simpler because HBase is kind of in the middle. It wants an LSM tree. Should you implement it just inside HBase or should you implement it inside this layer? So those are the things that are possible. The first one you mentioned is actually easier to do, okay? And in fact, I talked about it when we did federation. This never happened, but you understand what's going on clearly.
I got it. Maybe one more question. Sometimes performance is critical in the HDFS.
Yes.
Is it any ideas of using kernel driver, not user space driver, not Java driver, go to the closer to the OS hardware?
So two things. We do the following things. So we do send file. So most file systems include most Linux file systems, something called send file. So when I'm sending you data, okay, I can send data straight from the kernel. So in fact, the only thing that is holding back from doing that even better is the fact that HDFS is, what do you call them? Checksums are kind of in a separate file, not inline. In fact, if they were inline, it would be a simpler model. And so we do that. And we also have a shortcut to read the file directly, okay? And so that model does work and works pretty well. The part of what you're talking about is forget about the file system, go and create your own file system or layout on the disk. And that is actually attractive, but we need to see what the real benefit would be because suddenly there you are not getting this file system that has been well tested from Unix, okay? So that's one part. The second part is things like SSDs. The SSDs come in, the drivers and the way the file system uses storage is based upon how SSDs wear out different parts. All that work is a hell of a lot of work that we'll have to reinvent what Linux is doing. So if you go down that path, okay, to get that extra ounce and stuff like that, you have to realize that it's a hell of a lot of work.
Oh, yeah.
Okay, so it is possible, but we are not looking at that because we think there is already a fair amount of additional juice you can squeeze out by, for example, the better checksums, etc. Okay, the gentleman at the back.
What will be the impact on the name node memory consumption? For same number of blocks, how much memory will be needed?
Oh, okay, I see what you're saying. So, today, for example, to support 350 million files, you are using something like, I don't know, about 128 gigs or so. Okay, and if your working set is, say, a third of that, okay, then you would need a third of that memory. So, you could go to, a third of that, for example. Okay, I would say it would be silly to go to a name node less than 64 gigs because memory is so cheap that you really want to be able to make this part of the system to really fly. Okay, the only reason I think we would consider going to smaller memories if, for example, you want to run the name nodes on the data nodes. Okay, and so that's a model that a lot of people might find attractive, in which case you are competing with the memory of the application. So the application, they are fighting to get memory. If you're running Spark or you're running Hive with a lot of caching in, it's trying to fight for and get as much memory there. And the name node is saying, give me enough memory so I can cache my working set. Okay, and so that's kind of the balance you will have to do. But yes, you could reduce it. I don't see people going down to 2-3 gigs. Okay, I see more like minimum 32 gigs to 64 gigs. Okay, and you really want this part of the system to fly, to scale to a lot of clients.
Yeah, for
The
me,
guy at the
the
back.
most important question, do you have a timeline?
Uh, So we are in the prototype stage right now. We're building it. We think it's about a year to year and a half to go to GA. So in about 9 months, I think we will have things to play around in kind of alpha beta stage. Okay. So think about storage, for example, compared to my friends who work on the compute side and Jan and all that. If I tell you 5% of the tasks occasionally fail, restart them. I can't tell you 5% of your data blocks fail, please recreate your data. If I tell you that, you will say, bye-bye HDFS, okay? So that's the unfortunate part about storage, that it has to be rock solid, okay? And so unfortunately, I can't just say, here is the beta, bang, a month later, it is GA quality. So sorry, your question, I'll come back to you.
HDFS balance that works pretty neat across data nodes, but not within data nodes. hotspots on single disks because it is not distributed well within the data nodes. Is that going to be fixed in the future? And the other question is, how will HDFS balance work with the volumes?
The volumes that I mentioned? So let me answer the second one. It's an easier question because it actually fits in quite well that we will allow you to create volumes within a name node and then let you mount them. So you don't need to go to federation to get multiple volumes. And so it fits in extremely well, okay? And what we need to do is create a mount table and make sure things like ViewFS works well with all the. ViewFS is something that gives you a virtualized view of a mount table. That's a client-side mount table. And so that fits in very well. We can talk a little bit more afterwards because I thought I explained that, but clearly you're confused about something or I didn't explain it well enough. The second part on the hotspot, I mean, if you've got specific examples and issues you run into, you've seen that, please file a JIRA or talk to somebody in the community or to me, and we'll find out whether it is something specific. But generally what happens is HDFS actually balances the writes across the disks, okay? And precisely in order to balance, in fact, it doesn't do things like, let me just use the disk that is the least loaded, okay? And that's why, in fact, even in data nodes, we don't just go to the data node that's got the least amount of data and say, fill those up first, which would be the more natural thing to do. But as soon as you do that, you kind of get the hotspots that all your recent data goes there, or your current data goes there, and
That
becomes.
happen if you replace some disks that fail.
If you replace some disks that fail, what happens is you end up with very, very few disks, and so till the balancing happens. So yeah, it does happen in that case. So we've got I think there is work going on balancing the disks, okay, and moving data. And so what happens is till that time, all your writes still go across, and then your old data is still concentrated on the other disks. So yeah, it is not using the new disk to the full. But if it just starts putting the new data on the new disk, then what happens is it becomes the new disk becomes hotter instead of the old disks. So that's kind of the trade-off. Okay.
But there is work ongoing.
Yeah, there's work going on that. So somebody here, you had a question.
Real quick question. With the concept of volumes and underlying containers, will you also in the future introduce the thing called mirrors? We have a competitor that does that, and I hear that from time to time. Only because in a large cluster, you have say a set of data, and you want to, and it is hitting those nodes, right? A lot of people are hitting it, and you mirror that data. Now you have more opportunity. Instead of 3 replicas, you get 6, but it's an exact mirror.
So today we do offer you to easily go from 3 to 6, 5 to 8 replicas. So you could go to any files.
Yeah.
Okay, what we don't do is a way to expand the mirrors expand the replicas automatically. What would be good is HDFS said, you said 3 replicas good. It turns out this file or this block is being hit heavily. Let me go and expand it. So I say 3 is the minimum, but I will go to 4, 5, 6. I think that's a better solution than to have volume replication. So yes, we could do volume replication. I think with the problem you're talking about, it'd be better to solve that way. Okay, there's no current, the problem is there's so much work to be done, interesting things, but yes, that is something that we've not had people complain because most people, what they do is things like Hive and things like that, automatically will deal with that replication temporarily and shrink it. HDFS doesn't do it, so they kind of manage it within the application, but yeah, but it's a very good thought that you have.
Yeah, in HTTP we have a way of specifying tags to different machines to run SAS jobs or something. So is there a way to replicate a copy of the data to those specific machines?
So it's clearly possible to do that. We've been talking about adding labels to HDFS data nodes, okay? And so what we want to do is to have some sort of a balancer, things like that replicate data to those. For example, if you're running HBase and you have a failure, how do you make sure that the failover spot also has the second replica? Things like that. So that has come in. But you'd be a little bit careful if I say, for example, these files go to this data nodes and these files go to that. Then what happens is you no longer have your entire data set spread out. So you start getting hotspot, but worse what happens is you start getting failure. So as you reduce the cluster size, okay, and you don't distribute well, you're going to have more failures when multiple failures occur. Okay, so it's not as easy. I mean, technically it's easy to do some of those things, but what happens, the second order effects can be quite dangerous. So you need to think about that very carefully. Okay, so things like HBase and stickiness for HBase and co-location is what a lot of people have asked us for. So that's something that should be coming. Okay, like containers let us do that. Somebody had a question on this side? Okay, I guess not.
I was just going to ask one other question. So with the volumes and containers, would it make it easy to distribute your data to remote clusters?
So today we have something like DistCP. By the way, we want to change DistCP so there's no longer a MapReduce program but works inside HDFS. But I think what it'll let you do is you can say this volume, I want you to replicate with these policies, this volume with these policies. Clearly you can do that at the directory level. But a volume management becomes actually a better way to do it. Now, but there is actually disagreement in the community on that, to be fair, okay? A lot of people say, why do you need volumes? Directories are the same. Turns out they're not quite the same, okay? And so people who have done, talk to the operations guys that really get the value of management, the value of volumes and management. If you talk to a lot of engineers, they say, but what's the difference between a volume and a directory? So let me just do it anywhere. And so there's a debate that's going on right now. If you go and look at some of the JIRA sets. So that was the last question because my colleague at the back is telling me time is up. But I'm here for the next few minutes.